Right, going on to 5.7, separation of variables. Sometimes we have equations that have both a y and a y prime or dy dx in the same equation. This is called a differential equation. If this is the case, I'll show you what we do, but basic concepts are we work on separating the x's to one side and the y's to the other side, and then we integrate both sides with the respective variables. So to start off with, let's remember that these are the different forms of saying derivative, y prime, dy dx, and f prime of x. In this particular lesson, you'll be working mainly with these two on the left. We're going to start off with an equation, a differential equation. Dy dx is equal to x over y. Notice it involves a dy dx. When it involves a derivative, generally we call it a differential equation. So again, the idea is we're going to move the y's over here with the dy, and we're going to move this dx over here with the x. So all we really have to do in this particular case is multiply. We multiply both sides by y, it disappears over here and gives us y times dy dx, and we multiply both sides by dx, and it gives us x dx over here. So we wind up with y dy equals x dx. And now at this point in time, it's time to integrate with both sides. Interesting. So we're going to take the integral with both sides here. So same as you always have, power rule, 1/2 y squared plus c equals 1/2 x squared plus c. Now to clean it up, they do some things that's a little different, so I wanted to show you a couple of them. It doesn't matter where they add or subtract c's, you get c. It doesn't matter where they multiply or divide c's, they get c. Generally speaking, we don't know what constant is on each side, so they don't say that they cancel out if they subtract a c from a c. Notice that e to the x plus c, when you multiply like bases, you add exponents. So here I'm working backwards, but e to the c is just a constant. So e to the x plus c is often just described as c e to the x. Okay. So we're going to go 1/2 y squared plus c equals 1/2 x squared plus c to clean up this last problem. We just basically subtract the 1/2 x squared from both sides. We subtract c from both sides, and here's that bit we talked about. They just get a c. And then they multiply all the way through by 2. Every single piece gets multiplied by 2. Why is it not 2c? Because it's just a constant, so they just call it c. All right, a couple of reminders. We're going to work with some natural log and some natural exponential functions, and these things are inverses. So e raised to the ln x power is equal to x. This is the identity function. For that matter, also the natural log of e to the x is just x. Also a couple integrals. If we integrate 1 over y with respect to y, we get ln y plus c. And if we do happen to integrate e to the x, we just get e to the x plus c. So let's look at another example. In this case, y prime is equal to x times y. Well, again, this is a differential equation because we have it described with a derivative in it. We replace y prime with dy dx, and we basically do the same thing we did last time. We try to separate these variables. We multiply by dx on both sides. We multiply by the reciprocal of y, which is 1 over y on both sides. And in this particular case, it's similar to the last one, but I got the integration of 1 over y dy on this side, which is going to give us a natural log. So this is natural log y plus c is equal to 1/2 x squared plus c. We solve this for natural log y, and then here's a little trick we talked about before. Since natural log and e to the x are inverse functions, we take each side and we kind of bring each side as the power of e. So this is e to the ln y equals e to the 1/2 x squared plus c. So e to the ln y just cancels out and leaves me with a y. And e to the 1/2 x squared plus c, if I break that down, that's e to the 1/2 x squared times e to the c, which we just state as c e to the x squared over 2. All right, so there's a second one. And last but not least, an application of some sort. If we're talking an application, here's a differential equation. It involves a derivative over here, y prime. It says if it contains the original point 1, 1, what is the original graph? So you could ask what was the original graph. We could ask for slope of a tangent line here. If we wanted the slope of the tangent line, we would take 1 and 1, and we would plug 1 in for x, and we would plug 1 in for y, and this would be the slope over here, because again, y prime represents slope. And then to find the original point, the point is 1, 1, so that's not really too difficult. However, if we want to find what is the original line so we can figure out the equation, well, that's when we have to take dy dx is equal to negative 9 over x, or negative 9x over 16y. That's when we just substitute in. We push our x's to one side. We push our y's to the other side like we did before. We take the integral of both sides. Once we get the integral of both sides, we push all the x's and y's to one side and the c's to the other. In this particular case, we know that there's 2 places to sub in, so we just went ahead and put in 1 in place of y and 1 in place of x. And when we work this out, we find out that c has to be equal to 25 over 2. So the equation was 8y squared plus 9 over halves x squared is equal to 25 over 2. I looked in the back of the book, and what they actually had done was multiplied through by 2 all the way through, and that doesn't change the equation. It's just a scalar multiple. So looks something like 16y squared plus 9x squared is equal to 25. Here's some of the problems that we'll be doing on Tuesday. And that's all for today. Thanks.